Have you ever stopped to think about what actually makes a liquid electric? What's the difference between a liquid that can carry a current and one that just can't? Why can some of them light up a light bulb while others will leave it completely dark? Well, we're going to dive in and uncover the hidden electrical secrets of the liquids all around us.
It all kind of boils down to this classic question, right? You probably heard it in science class. You take some salt, dissolve it in water, and suddenly it's a conductor. But then you do the exact same thing with sugar, and nothing. They look pretty much the same, but one carries a current and the other doesn't. So what is the secret sauce? That's the mystery we're going to solve right now.
So, to figure this out, we're going to use a really simple experiment. Let's call it the glow test. It's perfect because we can literally see the answer. The brightness of a simple light bulb is going to tell us everything we need to know about what's happening inside these liquids on a molecular level.
The setup couldn't be easier. We just take a liquid, stick 2 electrodes in it, and hook those up to a battery and a light bulb. And here's the rule. If electricity can flow through that liquid, the bulb will light up. Simple as that. The brightness of that glow, well, that's our biggest clue.
Okay, let's kick things off with our first test. We'll pour in our first sample, something like molten salt, or maybe some dilute hydrochloric acid, and we'll flip the switch.
And bam, the result is immediate. It's powerful. The bulb doesn't just flicker on, it glows really, really brightly. This brilliant, steady glow is the classic sign of what scientists call a strong electrolyte. So what's going on here? Why is it so bright? Well, the compound we put in the water is literally breaking apart, or dissociating, almost completely, and it breaks apart into these tiny charged particles called ions. You can think of these ions as little couriers just zipping through the liquid, carrying the electrical charge from one electrode to the other.
And we see this happen with things like strong acids, think hydrochloric acid, strong bases like sodium hydroxide, and most salts like our molten sodium chloride or a copper sulfate solution.
So here's the key takeaway. When a strong electrolyte dissolves, that solution basically becomes a sea of these free-moving ions. It's like an electrical superhighway, and the current can just cruise right through without any trouble.
Okay, on to our next test. We're going to swap out that liquid for something different this time. Maybe a little acetic acid, which you probably know as the main ingredient in vinegar.
Now, when we complete the circuit this time, the result is, well, a lot less impressive. The bulb does light up, but the glow is really faint, kind of dim. And that's our telltale sign that we're dealing with a weak electrolyte.
So why the dim light? Well, it's because these compounds only partially break apart. Instead of every single molecule splitting into ions, only a few of them do. And fewer of those charge-carrying ions means a weaker current and a dimmer light.
Besides our vinegar example, this group includes other weak acids and bases. Things like carbonic acid, which is what makes your soda fizzy, or ammonium hydroxide, which is a common household cleaner.
So a weak electrolyte solution is a real mix. You've got a few ions floating around that are able to carry a charge, but they're swimming in a huge crowd of whole, uncharged molecules. It's like trying to drive on a superhighway that has almost all of its lanes closed. The traffic just barely trickles through.
All right, it's time for our final test. And this is where we get back to our sugar water. We'll also lump in other things here, like pure distilled water or even alcohol.
We flip the switch and absolutely nothing happens. The bulb stays completely dark. Not a flicker, not a glimmer. This means zero electricity is flowing. And that's what we call a non-electrolyte.
The explanation here is actually the simplest of all. These compounds, they dissolve just fine, but they don't dissociate. They don't break apart into ions at all. The molecules just spread out and float around in the water, staying completely whole and electrically neutral.
This is the group where our sugar solution belongs, along with a ton of other common substances like alcohol, kerosene, benzene, and yep, even pure, perfectly distilled water.
So, with these liquids, the solution contains only whole molecules. There are no free ions to act as those little charge carriers. Our electrical highway is completely closed for business. No ions, no current, no light. It's as simple as that.
Okay, so we've seen a bright light, a dim light, and a totally dark bulb. Now let's just pull back and put all 3 results together, because when you see them side by side, the powerful principle connecting them becomes crystal clear.
This table really just nails it. It lays everything out perfectly. What you see, the glow of the bulb, is a direct window into what's happening at the molecular level. A bright light means total dissociation, a solution full of ions. A dim light means only partial dissociation, a mix of ions and molecules.
And no glow means no dissociation at all, just a solution of whole molecules. So if you remember just one thing from all of this, let it be this. For a liquid to conduct electricity, it absolutely must have free-moving ions. That's the secret. And how many of those ions there are, well, that's what determines if it's a strong, weak, or non-conductor.
And once you get this, it kind of changes how you see things, right? This isn't just about chemicals in a lab. It's about sports drinks, tap water versus distilled water, vinegar in your salad dressing, even your morning coffee. Now that you know the secret is all about the ions, you can start to ask yourself, what other liquids in my daily life are strong, weak, or non-electrolytes just hiding in plain sight?